Joe, you can start.
Thanks. All right. All right, can everybody hear me at the back? All right, let's hear it. I'll use this. All right. So I'm going to basically go over what Ken did, but I'm going to just take a different approach. I'm going to take a slightly more mathematical approach. So how many of you guys know the equation of a line? Raise your hands if you know the equation of a line. All right, you should be all good, okay? So there's going to be no back propagation. We're going to use simple terms. But basically all you need to know is the equation of a line. So I like to think of a neural network as a way to approximate a function. So we have this red line over here, and that's our function we want to approximate. So a neural network basically approximates that function. It's a big, complicated photocopier machine. All right, so next thing we're going to do is basically, there's a bunch of different applications for neural networks. So there's regression, clustering, recommendation systems. But we're only going to cover it in the context of classification because that seems like a pretty popular area right now. So does anybody have any experience with classification? Can I see raise your hands? All right, what methods do you use? Josh? SVM. Have you guys all heard about SVM? Okay, so SVM is a linear classifier, and after this presentation, you should have a pretty good idea about SVM as well, all right? So this is what we're going to basically cover. So we have a data set, and then we use this data set to train the neural network. And then when we have some unknown sample right over here denoted by X, right? The image in Kent's example, we're going to use that X, we're going to feed it into the neural network, and then we're going to produce a prediction. Everybody got me so far? Very simple. So first we're going to cover this block over here, then the neural network, and the actual training we're going to do last, and we're going to do a very simple example for training. No back propagation, nothing complicated. So first thing we're going to do is denote our targets as y, and basically y can take on different values, so it can be 0, 1, or 2, and these targets can represent different things. And how many of you heard of the iris flower data set? I see somebody there. She raised her hand for a sec. 1, 2. All right. So the reason we're going to stick with the iris flower data set, it's a very simple example. So for this species of flowers, we're going to say y equals 0. And for this species of flowers, we're going to say y equals 1. And for this species of flowers, we're going to say y equals 2. So now I'm going to talk about features. So features are measurements that we can use to help us predict our class of. So for the iris flower data set, we have spetal length, and then we have spetal's width, and we also have petal length and petal width. So we want to use these features to help us recognize different flowers. So we have a training set, and over here we have a labeled example, and then we have a feature with it. So this is basically a labeled set of examples. So for this flower, it's in class 1 and has the sample 2, and we repeat the process, and we basically have a whole bunch of labeled flowers with associated feature vectors. So to get a better idea of what's going on, it's sometimes helpful to plot these features on the XY plane, on the Cartesian plane. So we have the class over here, and it's 0, and we denote it with a red color, and then we have the actual feature. So here's a second one, third one, fourth one, fifth one. What do you think the third one's going to be? What color? Blue? No. So this is usually the conventional way to define features, but in neural networks, I like to think we're kind of approximating a function. So what we do is we treat these features as samples of an actual function. And here's our actual function we're trying to predict. So we have x, our function, the argument of our function is x, and the output is y. So we can extend this to multiple dimensions. So we have different samples, and we're trying to approximate a function from these samples. So what do you guys think, if I pulled out a value over here, what color do you think it should be?
Blue.
Blue? And over here? Red. Yeah, you guys are really good. So the question is, do we have enough samples? And that's a question I'm not going to get into. But basically, we're trying to approximate a classification function. So it looks something like that, where y equals 0 and it's red, and blue y equals 1. Now, you can increase the number of classes. We're only stuck with a binary classification task for today, but it basically extends. And if you're a 3D person like me, you can visualize it as a big hump, where y equals 1. So we're just trying to copy this function. Everybody got me so far? All right. So one interesting thing is, if you actually plot out a real data set, you notice something very interesting. So this is flower 0 in blue. And what do you notice about flower 0? Josh? Compared to the second two flowers.
It's a little bit smaller spell, huh?
Yeah, exact. Oh, okay, spell length. That's good, that's true. So the spell length is a little smaller, right, over here. But one thing I noticed is it's easier to separate the blue flowers than the red and green flowers. So usually, adding more features gives us better classification ability. All right, and that comes at an expense, which we'll get into later. So the convention is, we have a data matrix. And the columns of the data matrix correspond to the features, and the rows correspond to the samples. And then we have a class vector. And I guys want you to pay attention for the first two, because you're going to tell me the color number 3. So the first row belongs to this class, second row belongs to this class, and where does the third row belong to? Or fourth? Give me the next color. Red? Okay, good. All right. So we don't have to use the measurements of the flowers. We can actually use the image of the flowers, and this is what Ken talked about. So images are comprised of 3 channels: the red channel, the green channel, and the blue channel, or the red channel. And each channel can be comprised of a set of numbers. And then we take these numbers and we compose a very large feature vector. So just a little side note, the method that Ken talked about, convolutional neural networks, they don't use this exact method, they use something similar. So now I'm going to talk about the linear classifier, which I like to think is the building blocks of a neural network. And what we're going to do is we're going to build a simple neural network out of a bunch of linear classifiers. So the equation of line in one dimension is given by this, and this generalizes to multiple dimensions as a dot product, and this also extends to matrices and convolution kernels. This is all linear stuff. So let's see what happens for different values of x. So let's take the following data set, right? And basically, the red samples will have the laser. The red samples over here are y equals 0, and the samples over here are y equals 1. So if we can use a line to separate the data, we can use this line to actually classify the data set. So here's the actual line we're going to use. Here's a picture of the line. So Z, as Ken mentioned, is the activation of a neural network. Keep that in the back of your head. So basically, if we plug in a value of x on this side of the line, our output of Z will be positive. And if we're on this side of the line, the output of Z will be negative. Everybody got that? Okay, you all say that, so I always say that too. So let's do a couple of examples, just so we get that into our heads. All right, so here's our function, and let's try for number 3. So we plug in Z equals 3, and what's 3 minus 1? 2. Let's see if you're right. Drum roll. Yeah, you guys are right. All right, now we have negative 2, right? And we plug it in, and we get negative 3. And that agrees with our initial statement. So the problem is we have these real numbers. We know that if you're on one side of the plane, you're negative, and if you're on the other side of the plane, you're positive. And we got to convert that number into an actual 0 or 1. Is there any ways to do that? Can anybody think of a way? So somebody said it? we can use a starts with I, if statement, right? But there's a little problems with the if statements. We want something in a functional form. So we use the logistic, we use the threshold function. So if z is greater than 0, we map it to 1. And if z is less than 0, we map it to 0. Everybody got that? So now we have our line, and if y equals 3, we map it to we use our line, and we get a value of 2. And our output equals 1. And if we use our second value, negative 2, we get a negative value, and then we use our line and map it to 0. Pretty simple, right guys? All right. So now I'm going to introduce the logistic function. So basically the logistic function looks a lot like the step function, except it's differentiable. And that's important for other reasons. So basically this is how it looks. When our value is very small, or negative, a very large negative number, we get a value close to 0. In the middle, or if it's also very large, we get a value close to 1. And in the middle, we're very close to 0.5. So now, what we do is if the value of z is greater than 0.5, we map it to 1. And if it's less than 0.5, we map it to 0. So let's do our example one more time. So we plug in 2, right? And because this value is about 0.75, it's greater than 0.5. We set it to 1. And we do the same thing for the second sample. Everybody got it? So, was that a question or discussion? No, wait. All right. So anything very close to the threshold is basically close to 0.5. And anything far away is close to 0 and 1. So this is good in 2 reasons. The first reason is if you're very close to 0.5, you're not very sure of your prediction. And another reason is when it comes to training, we're not going to get into this value. This property is very important for gradient ascent. But for now, because this is an introductory lecture, we're just going to look at it with respect to the actual prediction. So now we're going to cover the classification step. And this is going to be greatly simplified. And you won't even need a classifier to do this, but I think it'll give you a general intuition of what's going on. So I'm going to try to predict the value of y equals 1. Has everybody got that? There's not multiple samples, there's just y equals 1, okay? So, and I'm going to do this, the simplest model I can possibly think of. And our simple model is a simple constant. So before I do any math, what value for b would you choose? If I give you a 1 and you want to predict something, what would you say? 1, exactly, all right? So we need a cost function. So computers can't do that. So we need a cost function, as Ken said. So a cost function is a way for our, I guess, algorithm to say how good it's doing. So does anybody know any cost functions?
Gradient.
Who said something?
Gradient you said.
Root means square. Thank you. Who said that? Good, exactly. So this is not the best cost function. We're not even going to use it in our actual example, but I think it's very intuitive. It's differentiable as well, but that's not important. So here's our cost function, and we want to minimize this guy, right? And what minimizes this guy? What value for b? 1, okay, exactly. So we do the math, and that's our actual cost function. So now let's plot this cost function out on a graph. Over here, so what is the x-axis in the graph, guys? What is this axis? Well, no, it's not y, it's b, exactly. So this guy is a plot of b, and the lines we saw before are a function of x. So we have 2 things now, right? So the training part involves minimizing b. Does everybody got that? Right, okay, I found that really confusing when I was learning this for the first time. And where do we want our cost function to be? Am I getting warmer or closer, colder? Tell me if I'm getting warmer. Okay, I'm getting warmer. So we want a value of b that minimizes this guy. Everybody got it? So let's say so usually what we do is we start off with a guess. So let's start off with b equals -2. right? So this is bad. We want our cost function to be somewhere over here. So we gotta kind of push our value of b to be at 1. Everybody got that? Okay, cool. So we use the slope of the line, and then we have this thing over here called the learning rate. So this is chosen empirically, and you do this by experiments. And what's another name for a slope of a line? Starts with a D. Derivative, right? Okay, so I just use slope because by calculating the derivative is very important. We're not going to get into that right now. So just keep in mind that's the derivative. So what we're going to do is if we look at the slope over here, it's negative, right? And over here it's positive. So we're somewhere over here. So if I'm standing over here, right, and I know this way is negative, and you want me to walk positive, what would you multiply me by? A negative, right? So if I'm, a negative times a negative is a positive, so I would step this way, right? And the value for my function. How about if I chose a positive value? Which way would I go? That way. So that's exactly what we're doing. So basically, our next iteration for b will be b1 plus a positive number. And that's all gradient descent is. Now, there's different ways to calculate the slope, but funny, there's the Newton's method. But funny enough, with bigger data sets, they just use pretty much the exact same thing. The hard part is calculating this guy, but we won't get into that. So now let's do an actual example. So we start off with a guess equals negative 0.2. Now I predetermined this learning rate before to make it converge very fast. So we have minus 2 plus 3. And what's the new value of y? Y hat? Y hat equals 1, and our cost equals 0. Does everybody got that? So that's all those complicated neural networks are doing. They're implementing in the GPU. They're differentiating a much more complicated function. But this is the basics of what's going on. So you may be wondering why we do that. Oh, sorry, I missed a slide. So basically, in logistic regression, we replace the b with a logistic function. And sometimes, not always, we're basically minimizing it in terms of all the possible functions. You can actually minimize it one at a time, and that's called stochastic gradient ascent, if you hear that. But that's all gradient ascent is. We're just minimizing a function, and that's the actual learning part of most learning algorithms. So now, here we have a two-dimensional line, right? So my two-dimensional plot, so we have x1 and x2, and z at the top. So all we're going to do is draw a plane to separate these lines. So now, if we do the logistic problem, it starts to become apparent why we need an algorithm. Because if we try to minimize with respect to two parameters, it gets a little tricky. So neural networks that Ken mentioned have millions and millions of parameters, and that's why we need gradient ascent. So this is what actually is going on. So we start with the first iteration, and we see that these samples are misclassified. So we perform our first iteration of gradient ascent, and the decision line moves, right? And we're somewhere over here in the cost function, and we see these two guys are misclassified. So we repeat it again, and we have perfect accuracy. But if you remember the learning rate I said earlier, if it's too large, what happens is, basically, I'm over here, and I take a really big jump, and what happens is, our error actually increases. So choosing the learning rate is a big problem, but there's a lot of ways to simplify it. So one important thing that you should always do is your learning rate, basically your cost function minimizes your training data. And this is good, but this is more of a measure of how good your algorithm is in copying the data. So we need a second set of data to hold out, and we call that the test set. So that's a very important. So any questions before I move on? No? Okay, cool. So now, this is an example of a slightly more difficult problem. And this data isn't linearly separable. And before we move on to neural networks, I want to formulate this problem as well in terms of a decision function. So we want to either find a line that separates this data or copy that function. So in the terms of neural networks, I like to think about it as trying to approximate that black line. All right, so now let's talk about neural networks and compare them with linear classifiers. So here's the data that's not linearly separable. So does this line linearly separate the data, guys? Yes or no? No, how come?
No.
Right, because all these samples are misclassified, right? And let's see what happens when we apply the logistic function to it. We get something like this. And if we compare it to the actual function, we see that all these points over here are misclassified, right? So let's try another example, and we use this line. Does this line separate the data? No, how come? We see these samples are misclassified. So now, if we use a logistic function, we see that we should be getting a 0 right over here. So here's our actual function, and it's incorrect. So here's one logistic function. Oh, I just gave it away. And here's a second logistic function, and when we subtract them, what do you notice? What happens to this chunk?
Right.
0, right? So this chunk goes to 0, and does this chunk change? No. So there's our new function over here. So now we basically approximated our function using the 2 linear classifiers, and then we added another linear function on top of that, and then we applied another sigmoid function. So we just use a simple threshold, and we get our actual function. So this is a diagram that Ken showed. I didn't fill out the last part, depending on how many layers your network is. So basically, we have our input x over here. And then we have our 2 linear classifiers. And then we get 2 decision boundaries. And then we apply the sigmoid function. And we basically combine them together, not using really a linear classifier, but a linear function. And we get our function, our output function. Everyone understand that? So right now, we're about in the 1986 era of neural networks. We're not going to go into training, but around the same time, they basically showed that, hey, you can approximate any function using enough layers and enough the width of the network. So let's do a simple example in 3D. So here's a 4-layer neural network. And let's say we have this line, this line, this line, and this line, and we get the original function. This is our decision function. So to separate a line in one dimension, we needed 2 of these nodes. And how many linear classifiers do we need in this node? We need 4, right? So basically, as the amount of the dimensions of the feature go up, so does the basically amount of parameters you need. So one really interesting thing that happened is a much more interesting problem is if you start stacking these networks together, as Ken said, and you get a lot more abstractions in the data. You can approximate more complicated functions. And the problem with this is these algorithms basically were difficult to train. So we would take one layer and we'd stack it on top of another, and we'd repeat this process. But there was a problem. As these networks got bigger and bigger, they became harder and harder to train. And one of the famous terms is the vanishing gradient problem. So this problem was solved in, I think, 2006 by Geoffrey Hinton. And then that was like the catalyst of deep neural networks. And yeah, then around 2012, ImageNet happened, and that's when it started really hitting the I guess, mainstream. So before I continue or go on, or you're next? I have to, yeah. So before I go on to the demo, is there any questions? No? I forgot about the demo. All right. So I'm going to use TensorFlow. How many of you heard of TensorFlow? Okay, how many of you like TensorFlow? Oh, 1, 2, 3. Wow. Okay. All right. So I found. I think I'm using data science experience. So just in case the kernel dies, I have another demo over here I'll run, but I'm gonna try to do it in real time. So first thing we're gonna do is we're gonna load the data. So that's it, we loaded the data. And we're gonna import all the libraries. So NumPy and TensorFlow, TensorFlow's over here. And this is the important one, this is the one we're gonna focus on. The rest of these are just for giggles. So we loaded TensorFlow. So now these are some auxiliary functions that I did to make the code cleaner. So basically, our data set is we're going to determine college acceptance based on exam marks. Seemed like a pretty simple problem. And we're going to use the logistic function. Question?
Can I zoom in a little bit?
Yeah, sure. Thanks, Josh. Is that good?
Yeah.
All right. You can just... All right, so everybody familiar with pandas? Okay, so pandas is basically a data analysis library, for those of you who aren't familiar. And it's really useful for doing, I guess, the pre-part of machine learning, loading CSV files, reading databases, visualizing your data. So let's load our data using pandas. And for some reason, my kernel dies around this time. I'm not sure why. I think it's because it's Sunday. It always dies on Sunday. I think they do maintenance. Oh, okay, wait, let me try it again. It's okay, I already ran it before. I knew. So here's our data, and oops. I'm sorry. So here's our value of x, and the first feature is the exam score for number 1. And the second feature is the exam score for number 2. And the different rows represent the different people taking the exam. And the y is the acceptance rate. And if you remember from over here, 0 means not accepted and 1 means accepted. So what I did is I plot the data in a 2-dimensional plane. So in this plane, in the example, I did a 1-dimensional example, and z was the y-axis. Here, the y-axis is the actual exam scores. So exam score 2, and the x-axis is exam score 1. Everybody got that? I don't want you to get confused later when you look at this. So now, I'm going to split our data into training data and testing data. Oh, my kernel died, sorry. I wasn't supposed to split it. Take my word for it, it works. So now we train the tensor. We create a basically placeholder variable. And this is your actual variable you're going to use for training. So it's always good to print it, and you can see it's a tensor. And a tensor is a glorified matrix, basically. So we can see the size of the tensor. And in this case, a placeholder variable is our actual labeled examples, so x and y. So the next thing we're going to do is we're going to define our parameters. So theta 0 and theta 1. In this case, it's just exactly the same as the example we covered. And then we're going to use that, convert that to the output z, like I showed you. So finally, we're going to define our sigmoid, and TensorFlow has a built-in function called sigmoid function. So this line over here calls TensorFlow, and then the method sigmoid on z. So then we run our actual loss function, and it's basically, we're not using the mean squared error. You can use the mean squared error. That's your homework for tonight, convert this to mean squared error. So we're using we're using a Bernoulli loss function, and we're minimizing the likelihood. And then that's the standard practice now. For multi-class, it's called softmax function, but this is the simple case. So basically, we set our learning rate, which I discussed and we create a gradient descent object, and we minimize our loss function, which is over here. Pretty simple. So basically, Said, if you have more questions about like how TensorFlow works, you can ask Said. It creates a graph, and it does this for computational reasons. And when you want to actually do your processing, you have to start the graph. So we start the session, and then these are some variables I'm going to use to store our parameters for learning, are basically how well our algorithm is doing. So here's our for loop, and basically what we're going to do is we're going to run gradient descent for every feature in the group. So we're going to run it 70 times. So we use something called the feed dictionary to feed our actual variables into the object. And for every 10th iteration, we're going to print out the results. So here's our first guess of the line. Is this a very good guess? No. You can see that basically it's predicting these correctly, but it's misclassifying a lot of blue ones. So then here's our second iteration, right? So the line is actually moving in that direction. Then we do it again, and that looks a lot better. You see, if we compare it to the first one, our line has basically changed drastically. And then we repeated it one more time, and yeah, it's a pretty big, the top two on the right are now correctly classified. But this data isn't linearly separable, so there's nothing we can do after that, really. So now what I did is I put our learning rate, and what's the learning, our number of iterations, and our test error and training error. And as you can see, they pretty much track each other, but there's a couple of bumps over here and over here where they kind of didn't follow the rules. So that's the problem with neural networks. They tended to be very good at predicting our training data, but they failed at predicting our test data until Jeffrey Hinton and a bunch of smart people solved that problem. So any questions? Were you scratching your nose or asking a question? All right, cool. So I'll hold it back to Kent or Sean. Yeah.
Thank you very much, Joe.